Hello everyone. In this video, we shall briefly understand the pericyclic reactions and we shall solve the previous year KSET questions on pericyclic reactions. The organic reactions are mainly three types: polar reactions, radical reactions, and pericyclic reactions. Pericyclic reactions are the single step reactions. Reactants involve the formation of cyclic transition state and going to give the product. Reactions which involve in a single concerted step via the formation of a cyclic transition state involving the pi and sigma electrons. This is called pericyclic reactions. The key points of these pericyclic reactions are: there is no intermediate formation takes place. As in the polar and radical reactions, there is the intermediate takes place. In the pericyclic reactions, there is no formation of the intermediate takes place. Only there will be cyclic transition state. And solvents and reagents have no effect on the course of a reactions. In the solvents and reagents don't have the effects in the course of a reaction. And there are two conditions: thermal condition and the photochemical conditions. In the thermal conditions, the reactants are in their ground state. I mean, the reaction takes place in the ground state. In photochemical condition, excited state of reactants involved in the reaction. Okay, now we'll discuss about the types of these pericyclic reactions. There are three types of pericyclic reactions. First one is cycloaddition reaction, electrocyclic reaction, and sigmatropic reactions. First one is cycloaddition reaction. Cycloaddition means addition of alkene molecules. Addition of alkene molecules to form the cyclic compound. To form the cyclic product is called a cycloaddition. Means addition of alkenes to form the cyclic compounds is called a cycloaddition reactions. Okay, here the consumption of pi bond takes place and the formation of ni sigma bond takes place. There are two types. One is 2+2 cycloaddition reaction. Another one is 4+2 cycloaddition reaction. 2+2 means here the 2 pi electrons plus 2 pi electrons involved in the cycloaddition reactions and the formation of cyclic compound takes place. This is called a 2+2 cycloaddition reactions. Here diene and diene, here the diene means 2 pi bonds are there. Diene and dienophile undergo cycloaddition reaction to form the cyclic compound. Here this pi electron shifts here, this electron attack here, and this electron attack here, so that this will be the cyclic transition state. Through this cyclic transition state, you are going to get the cyclic product by the addition of two alkenes. This is called here the 4 pi electron system plus 2 pi electron system. Hence, this is called as 4+2 cycloaddition reactions. These reactions, pericyclic reactions, are based on F frontier orbital theory. Here, if the symmetries correlate, then only the reaction takes place, and then it is called as symmetry allowed. And if the symmetry is not correlate, then it will be called as symmetry forbidden, and reactions will not occur in a concerted way. There are two conditions: thermal condition and photochemicals. When it is 2+2 cycloaddition reactions, according to FMO approach, according to orbital symmetry of theory, this 2+2 cycloaddition reaction takes place under photochemical condition. In the thermal condition, it is forbidden. Under thermal conditions, we cannot have this reaction. 2+2 cycloaddition reaction is forbidden under thermal conditions, but it is allowed under photochemical condition. This is very important. These are the points to be remembered. These are the important points. So remember this: 2+2 cycloaddition reaction is allowed under thermal condition, allowed under photochemical conditions, but it is forbidden under thermal conditions. But 4+2 cycloaddition reaction is thermally allowed, but it is photochemically forbidden. Photochemically forbidden. Next type is electrocyclic reaction. It is a reversible reaction. Electrocyclic reactions are reversible reactions. When the molecule is having conjugated double bonds, the cyclization takes place to form the cyclic compound. Here the consumption of one pi bond takes place. Here this is the new sigma bond, and the consumption of this bond, this pi bond takes place. Butadiene, it is cyclobutene, and it is 135 hexatriene, it is 13 cyclohexadiene. These reaction can take place by both thermally or photochemically. Here also you can see these electrocyclic reactions can occur by both thermally or photochemical conditions. But another concept is the con rotation and disrotation, means the formation of this sigma bond by the rotation of this p orbital of these carbon atoms. When the p orbitals of these carbon atoms rotation takes place to form this sigma bond, so rotation of this p orbital of these carbon atoms, here it is these carbon atoms, the rotation of these p orbitals is important, then only you can form the sigma bond here. So here this is a 4 carbon system, these are the p orbitals. This is con rotation, means both the p orbitals are rotating in a clockwise direction or in a same direction. This is rotation, this is clockwise rotation, both the p orbitals are rotating in a clockwise, hence this rotation is called as con rotatory. And here this p orbital is rotating anti-clockwise, but this p orbital rotating clockwise, this rotation is called as disrotation. After the rotation, if the same orbitals, same type of lobes of these orbitals come on the same side, then the overlap of this orbital takes place and it gives the product. Here also you can see the after the con rotation, both the lobes of these orbitals, same lobes come in the same direction, means the overlap of this orbital takes place, same orbitals, then the bond formation takes place. The rotation of these bonds, this terminal p orbitals is very important. The electrocyclic reactions are depends upon the rotation of p orbitals of terminal carbon atoms. So here directly I will give the selection rules. Number of pi bonds, this is 4 pi system, 1,3-butadiene is a 4 pi system. When it is a 4 pi system, when there is a thermal condition, con rotation gives you the products. This is selection rules. When there is a 4 pi system like 1,3-butadiene, the rotation should be con rotation under thermal conditions. When you have the photochemical condition, it should be disrotation. Similarly, when you have 4n+2 condition, 4n+2 molecule, and thermal condition should be disrotation. Under thermal condition, disrotation takes place. Under photochemical condition, con rotation takes place. This is the selection rule of electrocyclic reactions. Then only it can give the product. 4n con rotation under thermal condition, disrotation under photochemical condition. 4n+2 disrotation under thermal and con rotation under photochemical conditions. Next type is sigmatropic reactions. Here it is a rearrangement reaction. Sigmatropic rearrangement reaction. It is a rearrangement reactions. Here the shift of pi electrons takes place and the cleavage of sigma bond and the formation of sigma bond takes place. Here this is shift of this pi bond. This sigma bond consumes and shift here as a pi bond, and this pi bond converted into sigma bond. This is 3,3 sigmatropic rearrangement. 3,3 sigmatropic rearrangement. It is 1, 2, 3. Here also it is 1, 2, 3. Here 1, 2, 3, 4, 5. This bond, this pi electron shifts here, this pi electron shifts here, this sigma bond breaks and it shifts here. There will be a new bond at 5th carbon atom. Hence it is shift of this hydrogen from 1 to 5. Hence it is called as 1,5 sigmatropic rearrangement. These are sigmatropic rearrangement reactions. These are the another examples of sigmatropic rearrangement. Here you can see the hydrogen of carbon 1 shifted to hydrogen to carbon number 3. Hence it is called 1,3 sigmatropic rearrangement. This reaction takes place under photochemical conditions. Here 1,5 sigmatropic 1,5 hydride shift takes place under thermal conditions. 1,7 thermal conditions. Like this, these are called as sigmatropic rearrangement reactions. This is a sigmatropic rearrangement reactions. It is called as Cope rearrangement reactions. Here 1,5-diene 1, 2, 3, 4, 5 1,5-diene under thermal conditions rearranges to another 1,5-diene by concerted. This is a concerted reaction. This is a concerted formation of 1,6 bond, breaking of the 3,4 bond. Breaking of this bond takes place. The bond between 3 and 4, breaking of this 3,4 bond, and migration of both double bonds in a 3,3 sigmatropic rearrangement. It is a 3,3 sigmatropic rearrangement type of reactions. This reaction is called as Cope rearrangement reactions. When the Cope rearrangement, in the Cope rearrangement reactions, when we have the alcohol groups, those reactions are called as oxy-Cope rearrangement reactions. Here the alcohol variants of Cope rearrangement. Here also same 3,3 sigmatropic rearrangement takes place. It is also thermally allowed, and these type of reactions are called as oxy-Cope rearrangement reactions. And when in the Cope rearrangement reactions, when there is a nitrogen is present in a diene, these type of reactions are called as aza-Cope rearrangement reactions. Here you can find that N is present in the diene system. Here also 3,3 sigmatropic rearrangement takes place. This also takes place under thermally allowed reactions. This is also Cope rearrangement reactions, but due to the presence of nitrogen, it is called as aza-Cope rearrangement reactions. Next important reaction is Claisen rearrangement reactions. This is also 3,3 sigmatropic rearrangements like Cope rearrangement, but here the oxygen or more heteroatoms are in the place of carbon. In the diene system, oxygen is there in the place of carbon. When the oxygen is there in the place of carbon, if it is 3,3 sigmatropic rearrangement and it is also thermally allowed, then this is also called as Claisen rearrangement. See, this is the example. Here oxygen is there in the place of carbon, and this is thermally allowed and 3,3 sigmatropic arrangement reactions. This type of reactions is called as Claisen rearrangement reactions. Here also we shall get to know about the two important reactions of photochemical reactions. Those are Norrish type 1 and Norrish type 2 reactions. This is Norrish type 1 reactions. These are photochemical reactions of ketones and aldehydes by fission of carbon-carbon bond adjacent to carbonyl group, and the elimination of carbon monoxide is termed as Norrish type 1 reaction. This is Norrish type 1 reaction. This is alpha cleavage of carbonyl compound takes place, favorable in vapor phase. Decarbonylation in various vapor phase is possible only when both the radicals are stable. Photochemical reactions of ketones or aldehydes by the fission of carbon-carbon bond adjacent to carbonyl group, and the elimination of carbon monoxide. Here the elimination of carbon monoxide takes place. Let's look at this. Here you can see alpha bond cleavage of alpha bond takes place, and the elimination of carbon monoxide takes place to form this product. This is called as Norrish type 1 reactions. Next important reaction is Norrish type 2 reaction. It is a photochemical reaction. It involves intramolecular gamma hydrogen abstraction followed by the cleavage of the resulting biradical to an olefin and an enol, which tautomerize to the carbonyl compound. This is just like the Mac-Lafferty rearrangement when the molecule is having gamma hydrogen. For Norrish type 2 reactions, the molecule should have gamma hydrogen, and it is familiar in the molecules which having carbonyl groups. This is alpha, beta, gamma. Gamma hydrogen must be present for the Norrish type 2 reaction. Here the abstraction of this hydrogen by this oxygen takes place. This electron of oxygen and this electron combine to form OH bond, and here the bond break, this beta bond cleavage takes place to form the fin, and the enol takes place. Enol is tautomerized to ketone again, and this type of reactions is called Norrish type 2 reactions.